guys, this is lesson 6.1, graphing systems of equations. In this lesson, we are going to determine the number of solutions a system of linear equations has, and we are going to solve systems of linear equations by graphing. But before we talk about those two things, let me show you a little video that introduces what a system is.
As the race begins, the hare, engrossed in a fascinating chapter in his algebra book, decides to give the tortoise a head start so that he can finish reading the chapter on solving systems of linear equations. As the race begins, the tortoise starts down the road at 1/2 mile per hour, a very brisk pace for a tortoise. We can graph the tortoise's distance from the starting point as a function of time, letting the vertical axis represent distance and the horizontal axis represent elapsed time. We see that in the beginning, when the elapsed time is 0, the tortoise's distance from the starting point is also 0. After that, since he is traveling at a constant speed, his distance increases linearly as a function of time. Since the tortoise's speed is 1/2 mile per hour, after 4 hours, he has traveled 2 miles. 4 hours after the race has begun, the hare finally finishes his algebra chapter. Even though the tortoise has obtained a significant head start, the confident hare decides to take it easy, since he knows that even casually strolling at 2 miles per hour, he will eventually pass the tortoise. So 4 hours after the race has begun, the hare is still 0 miles from the starting line. But from this point on, he travels at a constant speed of 2 miles per hour. Since the hare travels at a faster rate than the tortoise, the hare's graph has a greater slope. Looking at these two graphs, we see that throughout the race, the tortoise's distance increases linearly with time. And after 4 hours of elapsed time, the hare's distance also increases linearly. Until at some point, between 5 and 6 hours after the race has begun, the hare and tortoise meet. The point where the two graphs intersect represents the instant at which the tortoise and the hare are at the same place at the same time.
For this entire chapter, every time you hear the word systems, I want you to think, where do the lines cross? The whole point of this chapter is we have information and we want to put the information together and we want to find out if our lines on our graph cross and where do they cross. We have some vocabulary that we need to deal with. We basically have 3 situations we want to talk about. If we graph 2 lines and they cross, then we will have exactly one solution. The solution is, where do the lines cross? If we have this situation, we are going to call it consistent. Consistent means I have an answer. If there is only one answer, we are going to call that independent. If I graph my 2 lines and they actually turn out to be the same line, they lie exactly on top of each other, I am going to have infinitely many solutions. I still have solutions, so I'm going to call it consistent. But because I have infinitely many solutions, I'm going to call it dependent. I know these words don't even seem to make much sense, but they are the words that math people use, so we need to nail them down. Take good notes. If I graph my 2 lines and they are parallel lines, then I will not have solutions because they don't ever cross each other. I'm going to call that inconsistent. We say no solution and we call it inconsistent. You can find these words in your textbook on page 335. We're talking about systems of equations. We have more than one equation that we're putting together on a graph. if they cross or they lay on top of each other, they're exactly the same line, we will call that consistent. If there's only one crossing place, it makes an X somewhere, it's called independent. If it was the same line, we call it dependent. Independent means one solution, dependent means infinitely many solutions. If our lines in our system of equations turn out to be parallel lines, there will not be any solution, and we will call that inconsistent. Let's just look at a couple of situations that are in the textbook. In example 1, it says, use the graph of the right to determine whether the system is consistent or inconsistent, independent or dependent. So let's make notes of what color we're looking at here. Y equals negative 2x plus 3 is green. So we're looking at the green, there we go, line. And then y equals x minus 5 is the purple line. So we are looking at, do they cross? Well, yeah, they do. The green and purple cross right there. And so we are going to say consistent because, yes, they cross. And we are going to say independent because they only cross once. So this is consistent and independent. Okay, and in situation B, we have negative 2x minus 5. And you'll notice that that is red. And negative 2x plus 3, you'll notice that that is green. Okay, the green line and the red line are parallel like railroad tracks. They do not cross, and so we will say there is no solution. We will say that it is inconsistent. I know these words just don't have a lot of roots in the way we talk about graphs normally, so you just have to get used to them. Okay, looking at the guided practice here, 1A, y equals 2x plus 3 is blue. And y equals negative 2x minus 5 is red. Blue and red cross right there. And so we are going to say consistent because they do cross, and independent because it's only once. Okay, y equals x minus 5 is purple. And y equals negative 2x minus 5 is red. Notice that purple and red cross down here. So we are going to say that that is consistent and independent. Consistent, it does cross or overlap. Independent, because it only crosses once. Okay, when we solve by graphing, there's a couple things that are going to happen. Sometimes you're going to have to graph it by hand. And if you are graphing your lines by hand, you will want to put it in y equals mx plus b form, probably, because then you have a y-intercept and you have a slope that you can get your line easily graphed. Okay, these first two are in that format, but they've already graphed it for us, so we're just going to look at that. When I graph y equals negative 3x plus 10, that would be the blue line, and y equals x minus 2 is the red line, and we can see that those cross right there at the point 3 and 1. We will call that consistent and independent. Okay, in the second situation, notice that it's not in y equals mx plus b form. If you were graphing that by hand, you'd probably want to do some rearranging. They've already done the work for us. We can see those parallel lines, and so there is no solution to this. It is inconsistent, and that's all we need to say about that. I've already graphed one problem here. Let's see if I can remember which one that was. It was on page 338. It was number 10, and I graphed y equals 6. That's the purple line there. It's a horizontal line right through y equals 6. And y equals 3x plus 4 is the black line, and we can see that that does overlap. That problem actually asked us if it's consistent or inconsistent. This is consistent because, yes, it does cross. Is it independent or dependent? It's independent because it only crosses once. This one would be a little messy if we had to tell what the point was off of our own hand graph. The point is at 0.6 repeating and 6. So Desmos here, I put a link to this in Google Classroom, is a real is a real handy graphing calculator, because you actually don't even have to rearrange the equations like you would in a TI calculator or other type calculator. I can show you that here. If I graph number 19, I'd have x plus y equals 4. And in that particular problem, I have x plus y equals 4 and 3x plus 3y equals 12. And, oh, look at that. Oh, interesting. Okay, so when it's 3x plus 3y equals 12, the lines become the same line, right? Did you see that? They just overlapped right on top of each other. So yes, this is consistent, and it is dependent because it's really the same line. Okay, this was kind of fun because I could see that if it had been 3x plus 3y equals 1, they'd be parallel lines, and I would call this inconsistent. But as soon as it's 12, it's fun because those are actually the same line. You could see that mathematically. If I divided everything by 3, I would have x plus y equals 4, and then I'd have the same line. So it's actually just a different way of writing the same line. We call those consistent, but we call those dependent. So what did we learn today? We learned how to determine the number of solutions a linear system has by looking at the graph. If it crosses once, there is one solution. If it crosses all the time, it is infinitely many solutions. And if it's parallel, there are no solutions. We use fancy words for that. We say consistent if there are solutions, and we say independent if there's one solution, and we say dependent if there's infinitely many solutions because it's really the same line. And then the other solution or the other situation is that it could be parallel lines, in which case we will call that inconsistent. Hopefully you took some notes there. That's also in your textbook, so you can go back and look at that. The other thing we saw was that we can solve systems of linear equations just by graphing them, because we can look at where the lines cross.